Hello and welcome back. My name is Dr. Mark Taylor. This is Delaware Tech Physics 111, Lesson 6 continued. Lesson 6 is the third lesson of Unit 2 on forces and energy, and it's a continuation on the section on forces Part 3, which includes work and power. So in this section, we're doing one of the advanced topics that you're not responsible for. This is called centripetal acceleration. Now, some of you may have heard of centrifugal acceleration or centrifugal force. This is a little different, and this is actually the real force that centrifugal force is based on. But before we talk about the force, let's talk about the acceleration itself that's associated with the force. So the word centripetal itself, centra means center, petal means seeking. So centripetal literally means center seeking or seeking the center. And this acceleration always points to the center of a circle. So as an object is moving around the circle, the direction of the acceleration on that object is constantly changing, but it is always pointing towards the center of the circle that the object is moving around. And I'll illustrate that for you in a diagram in just a moment. So centripetal acceleration is a vector, like all accelerations, and it's right angles to the velocity vector. All right, well, you don't see a velocity vector right now. I'll draw it out, and I'll draw out the acceleration vector. It'll become a little more obvious what I'm saying here. But remember, when an acceleration is perpendicular to a velocity, it cannot increase the velocity. It can't make the speed greater, and it can't make the speed slower. It can only change the direction of that velocity. So this type of acceleration does not change the speed of the object. It is constantly changing the direction of the object, and centripetal acceleration is what is responsible for the object changing directions as it turns around a circle. So let's make a little diagram here to make this a little more obvious what's going on. Now, I've got a diagram right here, and you can certainly look at that, but I'm going to redraw this slightly differently. And let's make believe that at this moment in time, an object is going around the circle, and it's going around this way, counterclockwise. Well, at this very moment in time, if you imagine this thing was on a string and somebody was spinning it around, they suddenly let go of the string, this object would not continue to move in a circle. Newton's first law tells us that now that there's no net force acting on it, it would just continue moving the way it was moving at its last movement. Well, its last movement was to move this direction, because that is its momentary velocity as it's spinning around. The second you let it go, it'll just keep going in a straight line in the last direction it was moving. So if you imagine that this object is moving around in a circle because somebody's spinning it around, or for whatever reason the object is going around in a circle, you can imagine that when it is at this position, it is moving in this direction. But when it gets to this position, it's now moving in this direction. It's always tangent to the circle. And when it gets to here, it's moving in this direction. And it's constantly changing its velocity direction. Well, how can it be constantly changing its velocity? Well, if we imagine this is velocity 1, and this is velocity 2 here, and this is velocity 3, in order to go from velocity 1 to velocity 2, if we just think about how the velocity has to change its direction, it's changing its direction by bending towards this direction. And then velocity 2 is bending towards this direction to become velocity 3. Velocity 3 is bending that way. So you constantly have this acceleration in a direction that's always changing, that's constantly changing the velocity direction as well. And this looks confusing until you realize that each of these velocity changes or accelerations is pointing to the center of the circle. So as the object moves to its next position with its new velocity direction, it is constantly being altered in direction by an acceleration vector that points to the center. that are also changing in direction, but they are always pointing to the center of the circle. So the acceleration, while it changes direction every moment in time, its direction is always pointing to the center. It is always seeking the center. Hence, it is always centripetal, center seeking acceleration. So we call this centripetal acceleration, and we have a formula for it, where the formula for how big that acceleration is equal to the velocity that the object is moving as it's moving around the circle squared divided by the radius of that circle. So you'll notice a bigger velocity will result in a much bigger acceleration because the velocity is squared, and a bigger circle, meaning a bigger radius, means the acceleration will go down because this is in the denominator, whereas this is in the numerator of this invisible fraction. So acceleration is proportional, and this is the symbol for proportional, to the velocity squared. Whatever you do to velocity, you square that, and that tells you what happens to the acceleration. So velocity goes up, the acceleration will go way up. If the velocity goes down, the acceleration will go way down because of that squared. Whereas the acceleration, the centripetal acceleration, is inversely proportional to the radius. Inversely proportional to the radius. And that means that when the radius goes up, in other words, the circle gets bigger, the acceleration goes down, and when the radius goes down, the acceleration goes up. And you can think of it this way: as you have this circle where an object is going around it, and this velocity as it's moving around, we refer to this as the tangential velocity. You can just call it the velocity, that's fine. As the tangential velocity is constantly changing direction, but the amount of speed is the same at any moment, you take that value, square it, divide it by the radius, and you get how big the acceleration is. Now you can imagine if you have a small circle, you have to change its direction much more rapidly to get it to go in a circle. That's why the acceleration goes up when the radius goes down. If the radius goes down, smaller circle, the centripetal acceleration goes up. A small circle needs lots of changes very quickly to make it around that circle. Whereas a big circle, if you make the circle big enough, it's barely changing direction as it moves, so the centripetal acceleration is much lower with a big radius. And in this diagram of the little girl spinning a rock around, you see that she's spinning the rock with a string that is 2 meters long, so the radius of this circle is 2 meters, and the rock has a speed at any moment, that's referred to as the tangential velocity, because it's always pointing as a tangent to the circle as it's changing direction going around the circle. Its tangential velocity is 10 meters per second. Well, when we plug that into our formula for centripetal acceleration of v squared divided by r, we get velocity squared, which is 10 meters per second, and we have to square that value, and then we're going to divide that by the radius, which is 2 meters. Well, the quantity 10 meters per second squared is 100, and then we have to square the units as well, meters squared per second squared, and then we divide all that by 2 meters. Well, when you divide the numbers, 100 divided by 2, you get 50, and meters squared divided by seconds squared divided by meters gives you meters per second squared, which is always going to be our unit for acceleration. So this is our acceleration, 50 meters per second squared, and it is a centripetal acceleration. So this is how much the velocity changes constantly as it's spinning around in a circle. Well, that's how you calculate centripetal acceleration. Now let's look at centripetal force. So this is the force responsible for this acceleration that's always pointing to the center of the circle. Well, if the acceleration is always pointing to the center of the circle, then the centripetal force that causes it must also be always pointing to the center of the circle as the object is moving around that circle. So to calculate the centripetal force, it's actually pretty simple. Centripetal force is equal to centripetal acceleration times the mass of the object. But we know centripetal acceleration equals v squared over r, so we can also say that centripetal force is equal to mass times velocity squared divided by the radius. And of course, the acceleration is in meters per second squared if you want to use acceleration. The tangential velocity, like any velocity, is in meters per second, and the radius is going to be in meters. Now, one thing we haven't talked about is what is the source of this centripetal force? Well, the fact is there is no specific force that is the centripetal force. It's not like the force due to gravity or a normal force from a surface or frictional force from two objects rubbing against each other. Any force has the potential to become the source of the centripetal force. The name centripetal can be applied to any force, forces, or force component when that force causes an object to move around in a circle. And you can identify the real force or combination of forces that causes this rotational motion, that causes this centripetal acceleration by looking at each situation. And every situation is going to be different when an object is moving around in a circle. Here are some examples of forces that result in rotational motion that cause a centripetal force, resulting in a centripetal acceleration, resulting in an object moving in a circle. So when the Earth revolves around the sun, the Earth moving around the sun, the force that is constantly tweaking the Earth's velocity, the Earth would just go in a straight line and escape the solar system if there was not a force of gravity between the Earth and the sun. So that force of gravity between the sun and the Earth and the sun, is constantly tugging on the Earth, pulling it in such a way that the Earth ends up moving in a circular path around the sun. It's not perfectly circular, but it's pretty close. In the picture with the little girl spinning the string with a rock at the end of it, she's using the tension force on the string. She's holding the string. The rock is swinging around, so there's a tension on that string, and that tension is pulling in both directions along the string. But in the case of the centripetal force, it's the tension force pointing towards the center, towards the little girl's hand. That tension force is what's constantly forcing the rock to change its direction so that it ends up moving in a circle around the little girl. When you're running around a circular track, your running shoes have a frictional force with the track itself. And as you're making that turn around the track, friction of your shoes against the track are what allow you to turn your body as you're rounding corners on the track. So that friction force becomes a force pointing towards the center to curve your movement around the track. So this frictional force is now the centripetal force, causing centripetal acceleration, causing you to move in a circular pathway. The next example is using the normal force in a loop-de-loop track. If you're not familiar with a loop-de-loop track, that's a vertical circular track where the track makes a loop, and you might see these in a roller coaster ride. You might see these in a trick show for a motorcycle or cars, and the vehicle will ride along the track at enough speed so that they can go all the way around the loop. Well, one of the the reasons they're allowed to go around that loop without falling is the track is always applying a normal force up from the track, a support force from the surface perpendicular from the surface. Well, when you have a surface that is circular and you're constantly making normal forces that are perpendicularly up from that circular surface, you end up with a lot of forces that are all pointing towards the center of the circle. And these normal forces are pushing up against the car and allowing the car to constantly change direction as it's making its loop-to-loop around this track. The next example is the X component of a tilted normal force. That sounds pretty complicated, and it's certainly more complicated than you need to know for this course. But this is what happens when you're on a highway and you're riding at a very fast speed and you have to make a turn on the highway. The highway is curving. Well, if the curve of the highway is a very sharp curve, sometimes you'll find that the highway itself is not flat, it's actually tilted, it's on an incline. And the reason for that is as somebody is going around this loop, the surface itself is lifted up so that the outer edge is higher than the inner edge. And you see this a lot in racetracks. It becomes very exaggerated in racetracks where cars are going as fast as 200 miles an hour, and in order to keep the cars on the track as they're making a turn, the curves of the track are elevated on the outside of the track, tilting down towards the center of the track, and this allows a normal force pointing from the track in such a way to keep the cars from skidding off the edge of the track and making the proper turn around the track. And the last example here is similar to the force of gravity keeping the Earth revolving around the sun. You can also have electric charges orbiting other electric charges using electrostatic force. So you can imagine a negative charge orbiting a positive charge with an attractive force between them. And as the negative charge is moving potentially in a straight line, it's being pulled towards the positive charge. So here's the positive charge. Here's the negative charge moving this way, but it's being pulled this way towards the center. So it will change direction and will constantly change direction, resulting in a circular pathway around the positive charge. So let's take a look at some problems involving centripetal force. Number one, consider a 1,000 kilogram satellite, all right, that's its mass, in a circular orbit around the Earth. The satellite orbits at a distance of 1.28 times 10 to the 7 meters above the surface of the Earth. The mass of the Earth is 5.972 times 10 to the 24 kilograms, and the radius of the Earth, that is the distance between the surface of and the center of the Earth, is 6.371 times 10 to the 6 meters. What is the force of gravity on the 1,000 kilogram satellite? Hint, what distance do you use? Remember, the satellite is above the surface. So this is ultimately going to be a centripetal force problem, but remember, centripetal force has to have a source of force, and in this case, the satellite is held in a circular orbit by the force of gravity, which is also the source of the centripetal force, allowing the satellite to move in a circular path around the Earth. So let's do a little diagram here. We've got the Earth, and it has a certain radius. We'll call that radius 1. And the satellite is at an additional distance away from the surface. We'll call that R2. So the distance to the center of the Earth is the sum of those two distances. Call that R total. And that's going to be the sum of the distance above the Earth and the radius of the Earth. We have to add those two to get the distance between the satellite and the center of the Earth. Remember, force of gravity, when you do the calculation using Newton's law for universal gravity, you need the distance between the centers of the mass. Well, the satellite's so small, we don't have to worry about the center of the satellite, but we do have to worry about where the center of the Earth is. So what's the formula for gravitational force? It's capital G, which is universal gravitational constant, times the first mass, which will be the mass of the Earth, times the second mass, which will be the mass of the satellite, divided by the distance squared. Well, it's the sum of those two distances. It's R1 plus R2, and we have to square that quantity. So let's plug in our values here. We know that G, the universal gravitational constant, is 6.674 times 10 to the minus 11 Newton meters squared per kilogram squared. We know the mass of the Earth is 5.972 times 10 to the 24 kilograms. And we know the mass of the satellite is an even 1,000 kilograms. We're going to divide that by the distance between the satellite and the center of the Earth, which is the sum of the two distances we discussed, and we have to square that value. So the two distances are the distance above the surface of the Earth, which is 1.28 times 10 to the 7 meters, and then additional distance from the surface to the center, which is the radius. That's another 6.371 times 10 to the 6 meters, and we're going to square that sum. When we add those two distances together, we get 19,171,000 meters. That's the total distance from the satellite to the center of the Earth. We have to square that value in the formula. So we're going to multiply the three numbers on the top and then divide it by this number squared. And when we do that, we get a value of 1,084. And our units are newtons because we are calculating a force. So the force of gravity between the Earth and the satellite is 1,084 newtons. And then looking at part B, it says, what is the only source of centripetal force on this satellite? Well, remember, the satellite is in orbit around the Earth. The only force on the satellite is the force of gravity from the Earth as the satellite is moving around in a circle. Now, the satellite's trying to move in a straight line at any one moment in time, but the force of gravity is constantly tweaking the direction of that velocity, so the satellite ends up making a circular orbit around the Earth. So the only source of centripetal force is the gravitational force. And what that means is the centripetal force is also 1,084 newtons. In other words, by solving for gravitational force, we've solved for the centripetal force in this particular situation. Part C says, what is the centripetal acceleration on the satellite? Well, we've just determined the centripetal force on the satellite. Centripetal force is 1,084 newtons. And we know the mass of the satellite is 1,000 kilograms. We're now asked to determine the centripetal acceleration. Well, we have two ways to do that. One way is to use the formula for centripetal acceleration, which equals the tangential velocity squared divided by the radius of the circle that the satellite is moving in, not the radius of the Earth, the radius of the circle. So that's the sum of the two distances we talked about before. And we have a way to easily calculate the sum of those two distances. We already did. It's about 19 million meters. The problem is we have no way to get the velocity right now. So we have to look for another way to solve it. Well, we also know that the centripetal force is equal to mass times centripetal acceleration. When we know the centripetal force, that's 1,084 newtons, and we know the mass, that's 1,000 kilograms. So we can use that to determine the centripetal acceleration. So centripetal acceleration is just equal to the force, which is 1084 newtons, divided by the mass, which is 1,000 kilograms. We pull out our calculator, or we just divide by 1,000. We get 1.084, and it's acceleration, so we know our units are going to be meters per second squared. And that's our centripetal acceleration. In which direction is the acceleration acting? It's always acting towards the center. It's constantly changing where it's pointing from, but it's always pointing to the center. That's what makes it centripetal, literally center seeking. Part D says, at what speed, that is the tangential velocity, is the satellite orbiting the Earth? Well, now we can use this other formula for centripetal acceleration. Now we know the value for centripetal acceleration. We don't know the tangential velocity, and we do know the total radius of the circle. So let's plug in some numbers and solve for velocity. We know that our acceleration from two problems back is 1.084 meters per second squared. We know this equals our tangential velocity squared, our unknown value. And that's divided by the radius of the circle that the satellite is traveling in. The radius of the circle it's traveling in is the distance from the satellite to the center of the Earth, which we determined on the other page is 19,171,000 meters. Multiplying both sides by this value, we get 1.084 meters per second squared times our 19,171,000 meters, and that will equal our velocity squared. Multiplying these numbers together, we get 20,781,364, and we're multiplying meters times meters per second squared. That gives us meters squared per second squared equals our velocity squared. To solve for velocity, we have to take the square root of both sides. Technically, we would take the plus or minus the square root of both sides, but we're only going to use the positive value for velocity. So our velocity, taking the square root, is equal to 4,559 meters per second. And that's our tangential velocity for the satellite.